We've just looked at how we can take a quadratic function, ax squared plus bx plus c, and rewrite it in vertex form, which is a process called completion of the square, and it allows us to determine lots of important properties of the function. So let's now kind of list lots of important properties of quadratic functions. The quadratic functions, and let's have them maybe in standard format, ax squared plus bx plus c. Maybe in vertex format. Vertex form is of the form, well, you can always write it with an a at the front here, x plus d squared plus b. So before I did this little a with a capital A, but I might as well write it with little a because it is actually equal to this. Finally, I suppose we could also do a factorized form. And in factorized form, it would look like, you could take the a out, it would be x minus r1 times x minus r2. So this last case may not always be possible. It depends on a few factors. So factorized form. Brackets, this is if possible. Not every quadratic equation can be factored, not over the real numbers. Okay, so I want to look at properties of these. So let's go through our list of properties. First is, what about domains? Well, thankfully, these are polynomials. Domains make sense for anything at all. So the domain is everything, minus infinity to infinity. There's not much to say there other than the fact that it's just because x squared plus, or ax squared plus bx plus c makes sense for any x. Of course. Next, range. So we've already seen that the standard format, which is the first, so this is kind of the standard form, and this is the vertex form. The standard form isn't very good for this, right, because it's pretty opaque what the output of the function is, but the vertex form turned out to be very useful. So the following is true. The range, well, it kind of splits into two possibilities depending if a is positive or negative. So if a is positive, the range turns out to be everything from b onwards, inclusive of b. And if a is negative, remember I'm assuming a is non-zero in all of this because it's a quadratic equation, then it's kind of the other way around. So it's from minus infinity to capital B, inclusive of b. So why is this the case? Well, the vertex form really tells you the format of the graph. So if I was to graph, for example, if I was to graph a parabola given by, so remember, a parabola is our name for a graph of any quadratic function. So if I had, let's say, y is equal to 3x minus 2 squared minus 1. Well, if I took the time to work out what this graph looks like, it would actually look at the following. I would have kind of a lowest point here at minus 1, and it would almost be centered, if you want, at 2, because I'd have had to move to the right by 2. So we've got a kind of a 2 there. So what this would look like would be the following. It would look like, just make sure I've not gone mad here. Yes, it's going to look like this. The scale may not be perfect, but that's kind of the vague shape of it. Okay, so this point at the bottom is the coordinate is 2 comma minus 1. 2 comma minus 1. So this is one of the reasons it's called the vertex form, is because the format kind of gives you what the kind of the coordinate is at kind of the tip. And because it's 3, it's kind of a parabola which is going upwards. So we can just read the range off here, can't we? Right? The range is all things which are greater than or equal to minus 1. So it's everything past this point. So we can read the range off. So the vertex form is very good, right? So in this case, the vertex form has told us what the range has to be. So the range is equal to minus 1 onwards in the positive direction, inclusive of minus 1. All right, so next, well, we've got similar kind of story with increasing or decreasing. You can see here that overall a quadratic equation is not going to be increasing or decreasing, not overall on the domain, but if I restrict the domain to be on either side, in this case of 2 in this example, you can see I'm increasing on the right of 2 and I'm decreasing on the left of 2. So that turns out to be true in general. So this is going to take a bit more time. So if A is positive, the parabola is kind of like a U. So if A is greater than 0, this implies that F is decreasing before I get to the vertex. So this would be on the interval minus infinity to, I think the position is minus D. So does that fit with this story? Yeah, I suppose it does, because here D is minus 2, so minus minus 2 is 2, that's that position there. Okay, and it's increasing afterwards. On the interval from minus D onwards. Perfectly reasonable. And we've included square brackets for the inclusive of the minus D and D because it's an overall statement about the whole interval. So we never really talked about the idea of increasing or decreasing at a single point, right? That's a complicated idea. It's not one that's going to be brought up in pre-calculus. It's something you're going to study in calculus. We've only got the idea of increasing or decreasing on, let's say, an interval or something like that. So it's totally correct here, right? If I am on only this part, inclusive of the bottom onwards, I'm increasing, right? If I move from left to right, I'm going up. So it's perfectly fine to include the bottom, in case you're wondering. On the other hand, if A is negative, it kind of turns around, then F is increasing before. So it's exactly the same, but the decreasing and increasing are swapped. Okay, so maybe I should do an example just to illustrate this. So let's do graph as always. It's a good plan to see graphs of all of this stuff, so we'll do the following. And let's do y is equal to, I don't know, let's do minus a half. Is this a nice one? Yeah, we'll do one that's different than the one above. So minus a half times x plus 1 squared plus 2. So in this case, the vertex is at minus 1, 2. So we've got minus 1 here, and it's kind of 2 up here. And it's upside down because of the fact it's a negative. So this is the kind of the top. Is that right? Something like this. Okay. So here A is negative. So I should be in this position. Is that correct? Well, yes, right? Before I get to -1, I'm increasing. And then after -1, I'm decreasing. So perfect. This fits exactly with the story. And you can see why the A is important, because if I was to choose a positive A, it would be upside down, like the one above, and then the story would be reversed. So again, without this being in vertex form, it's ridiculously difficult to do this, right? If I just gave you something in standard form, how on earth are you going to work out if it's increasing or decreasing? So in this case, your A is equal to -1/2. That's negative. Next, even or odd. Well, this is more straightforward and something we could have done before without any of this vertex form. In fact, the standard form is much better for this. So F is even if and only if there's no linear term. So B is equal to 0. And F is never odd. The reason it's never odd is because you've always got the square piece. A is non-zero, so ax squared is always there. And we always know that if I have a polynomial, it's an odd function if and only if all of the powers are odd. And it's an even function if and only if all of the powers are even. So may as well do a quick example visually, no harm, just to illustrate why. So if I gave us the graph y is equal to, I don't know, let's say -2x squared plus 1, that would look like the following. So the basic thing is if b is equal to 2, the vertex is centered at 0. So it looks like something like this. In this case, it would be something along these lines. Dot, 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 dot. Is that right? So we've got a 1 up here. So this is the same after reflecting on the y-axis, isn't it? Which is what you want visually for an even function. We could have done this purely algebraically, feeding -x into it and seeing what happens, seeing it doesn't affect it, but let's do a graph because it's always nicer. Or at least it's always nice to have a good visual understanding. So this is the same after reflecting across the y-axis. Nice. So finally, let's think a little bit about X-intercepts. So X-intercepts correspond to zeros of quadratic expressions, which we know is kind of an interesting topic. It's one of the first things you study in detail about quadratic expressions is finding zeros. So of course, by far the best way, the best possible scenario would be if you have a factorized situation. So if you had kind of ax minus r1 times x minus r1 is equal to 0. This, of course, is if and only if one of the factors is 0. A is non-zero by assumption. So either x is equal to r1 or x is equal to r2. So the factored form is beautiful, right? This is giving the x-intercepts. So maybe I'll just make sure we understand we're doing x-intercepts. So factorized form is very nice, but we all know factoring can be pretty difficult. Factoring, there's a bit of trial and error involved. It may be basically impossible to do. However, the vertex form is a super powerful way of doing this, and it gives rise to something you are most definitely familiar with. So if we're doing with the vertex form, well, what would we have? We would have ax squared plus bx plus c is equal to 0. That's what we need to find the x-intercepts. But this is if and only if, well, if I put it in vertex form, x plus d squared plus b is equal to 0. And just like the example in the last video, we can actually solve this now by doing basic algebra. So if I do this by basic algebra, what happens? Well, eventually, I can write it down in this specific case, I suppose. You'd end up with x is equal to, it'd be a bit of a mess. It would end up being, I think, minus d plus minus the square root. So I'm jumping through quite a few steps here. I'm kind of cheating. I shouldn't really be doing this, but it's not so important. That's why I'm doing it. But b divided by a. So, of course, this would only work if b was positive. Oh, sorry. Got it wrong. It's got to be minus b. So this would only work if b was negative. Right? Otherwise, we'd end up with the square root of a negative, which doesn't make sense for real numbers. But why have I told you this? Well, if you were to take the time to do this and translate everything back into little a, little b, and little c, you would end up with the following. This would be x is equal to minus b. So this requires kind of painful algebra to do, but it's just algebra with exponents. There's nothing too profound about it. The square root, something you're very familiar with, b squared minus 4ac, all divided by 2a. So that basically requires you writing down d and minus b in terms of a, b, and c. Little a, and little b, and little c. And if you do that and simplify, eventually you get this. So this is very familiar to us. This is the quadratic formula. So the quadratic formula really is, it's a consequence of the completion of the square. Going from standard format to vertex format allows us to find zeros, and that's what the quadratic formula is. It's some sort of brutal shortcut through all that process. So let's do it, right? Let's do an actual example. So let's imagine I have 3. So imagine I have, where are we? So 3x squared minus 12x plus 6 is equal to 0. So I'm actually going to complete the square here. So if and only if, let's bring out 3, x squared minus 4x plus 2 is equal to 0. If and only if, okay, so now I've got to go through the business of completing the square. So this would have to be 2d. So d would have to be equal to what? It would have to be equal to minus 2. So I need to do a plus and minus of minus 2, or minus 2 squared, d squared. I'm going fairly quickly here. This is 3. It would be x minus 2 all squared. That would give me x squared minus 4x, of course, by foiling. But then you'd be adding a 4. So we need to take that away. And then, of course, add the 2 at the back. It's equal to 0. So now this is if and only if what? 3. So maybe I should do this with a full square bracket just to illustrate exactly how everything fits. It can be hard to kind of spot how they go together if I don't write it like this. So this is now 3 times x minus 2 squared. Okay, what's it going to be? Minus 2 now. It's equal to 0. Suppose if I want to do all of this totally fully, I could factor this out. It's kind of unnecessary at this point, but x minus 2 all squared minus 6 is equal to 0. So that's in my vertex form. So now this is if and only if x minus 2 squared is equal to, well, 6 divided by 3, which is 2. So this is if and only if x minus 2 is plus or minus the square root of 2. And finally, you're going to add 2 to both sides. So this is if and only if x is equal to 2 plus minus root 2, as you'd expect. Cool. So it's up to you which you'd rather use. The completion of the square business is, it feels more difficult, I think, to most people. Most people look at this and think, well, can't I just plug it into a formula? I think my general advice in these kind of situations is you want to understand why the formula is true, right, before you just blindly memorize it. Because if things are ever so slightly different than the standard format, you're in massive trouble. Whereas if you understand completing the square, you'll never be lost. So there's kind of a trade-off here. It's difficult at the start to understand completion of the square, but once you do, you're kind of fireproof. Whereas if you just memorize a formula like the quadratic formula, I mean, if I give you something which is a bit more non-standard, then you may be completely lost. That's just kind of general advice about formulas and stuff like that. You don't want to kind of blindly memorize them. You want to kind of understand the mechanics behind them. You'll find that when you do exams at the university level, especially, you'll be tested on things where it may be more subtle than the standard case. So you've really got to understand kind of the smaller mechanics behind what's going on. You can't just apply the same formula every time like you can in high school. You're probably going to be given examples or problems where it's slightly off-piste, a little bit different than you're used to, and you can't just apply the standard method. So you need to really understand what's going on. Okay, so that's a pretty comprehensive overview of the properties of the quadratic functions that you'll need at least when you go into do calculus. I think I should do a summary of each of the standard formats at this point. So if I give you a quadratic function, as I've said, there are three basic ways to express it. There's the standard way, there's the vertex format, and finally there's the kind of factored format, if possible. So this is the standard form. So that's ax squared plus bx plus c. There's the vertex form, which is, well, capital A in general, but it's always the same as this is little a plus d squared plus b. And then there's the factored form. And this is only if possible, right? So it may not be possible. Not over the real numbers anyway. So what's the factored form? Well, it's the one I wrote down before. A times x minus r1 times x minus r2. That's kind of the neatest way to write it. So there's not much that you can get from the standard form. The standard form, I suppose you get the following. The sign of A tells you if you're a U or an upside down U. So if A is greater than 0, this would imply it looks like that. If A is less than 0, it would tell you look kind of upside down, so you look like that. And I suppose the only other thing is, well, we can read off the y-intercept reasonably easy. So if I feed in 0, I obviously get C. The vertex form, way more powerful. In this case, the vertex form tells you much more about the structure, because you have the same basic story as this, but you know kind of what point that kind of top or bottom is, which tells you a huge amount about things like increasing, decreasing. So in both cases, this position is minus d comma b. Minus d comma b. So that's really useful. And I suppose for the last case, what you can really read off here, other than the A telling you if you're upside down or not, this is the X-intercepts, so you can read those off fairly painlessly. So each has the benefits, disadvantages. The most powerful is the vertex form, I think, because you can read off so much. You can find the X-intercepts by kind of doing a quadratic formula type algebra business. You can read off increasing, decreasing, all this kind of stuff. So this is a kind of a good summary of what quadratic functions look like, the different formats they come in, and why each of them is useful.